So as we've just discussed, in order to solve the flight path equations, we actually need the Euler angles in terms of the angular velocity components. So to do that, we're going to use the kinematic equations. So we have our angular velocity vector, omega, and we can write that angular velocity vector as basically changes in the Euler angles with respect to time, right? So omega, which is p, q, and r, the angular velocity components about the x, y, and z axes, we can write that as the change in Euler angles about those axes. So what we know is that the first transformation, which takes us from the subscript 1s to the subscript 2s, is a rotation about the z-axis, which is the vertical axis pointed vertically downwards. And if we're rotating about that axis, right, let's get dusty. So if we're rotating about the z-axis, we're yawing. So we're not changing that z-axis when we make the transformation from the subscript 1s to the subscript 2s. So that means the subscript z1 and the z subscript 2 are the same, which tells us that our unit vectors in those directions are the same also. So therefore we can write our change in psi, which is our rotation about the z-axis, like this. So we take the change in Euler angle multiplied by the unit vector in the z direction, which we've just said is the same as the unit vector in the z direction in the next sequential intermediate coordinate system. And we can do that for each of the rotations, so about the y-axis and about the z-axis, so in pitch and in roll. So therefore we can rewrite our angular velocity vector in terms of changes in the Euler angles multiplied by these unit vectors in these intermediate coordinate systems. So the way this works out is that the I bar is actually the final coordinate system, the one in the body axis system, but these two are in our intermediate coordinate systems, which go along the way of our sequential application of our Euler angles. So we need to actually write these two unit vectors in terms of the normal I bar, j bar, k bars, right? So we may apply the same transformation to the unit vectors as we did to the velocity vectors, right? So you remember we applied matrix transformations to the subscript 3s to get the 2s, and the regular u, v, and w components to get the subscript 3s. So we can also do that applying the same matrix transformations to these unit vectors, right? So to the subscript 3s to get to the 2s, and from the regular I bar, j bar, k bar to get the intermediate coordinate system with the subscript 3s. And that looks like this. So we can use these matrix transformations to find what k2 bar and j3 bar are in terms of the regular I, j, and k bars. So if we look up here, we need to find what k2 bar is. So we look up here, we say k2 bar is basically the negative sine of theta multiplied by I subscript 3 bar, nothing in the j3 direction, but then cos theta in the k3 direction, which is what I've written here. And then we can further use these matrix transformations to replace what these subscript 3s are using the second matrix transformation, right? So I3 here, we just look up in the second matrix transformation, is simply I bar, right? So that just changes that I3 bar to just I bar. Then K3 here, we look up in this second matrix transformation, is 0 in the I bar direction, it's sine phi in the J bar direction and cos phi in the K direction. So that's what gets replaced into here, and then we can multiply out those brackets. We can also find what our, where are we? Over here, we can also find what our J3 bar is from this second matrix transformation here. Well, it's 0 in the I bar direction, it's cos phi in the J bar direction, and minus sine phi in the K bar direction, which is what I've written here. So we put all of that together back into our angular velocity vector, this one. So we have the change in psi multiplied by K2 bar, which we just worked out as this, theta dot multiplied by the K3 bar, which we've just worked out as this using those matrix transformations, and then we just have this phi dot I bar on the end here. So what I've done from there is just group all of the I bars, J bars and K bars together to get this, and then written it in matrix form. So that's matrix form, which takes us from omega and its components P, Q and R to the changes in the Euler angles. But what we actually want to find here is this system the opposite way around. So we want to find the Euler angles, or the change in Euler angles, from the angular velocity vector PQR. So we actually need to take the inverse of this matrix transformation and apply it to the components of the angular velocity vector P, Q and R, which is that. And this is the definition of the kinematic equations, and it's how we find the changes in psi dot, theta dot and phi dot. But there is one problem with this system of equation, and it is that there are singularities. So the solution to this equation blows up if theta or phi are 90 degrees, right? Because tan of 90 degrees tends to infinity, and so does the secant of 90 degrees. So that's a big problem if we're trying to run a simulation, say, on the computer, which tries to solve for an aircraft doing a loop or a barrel roll, for example, because we pass through these angles, right? So that is a big problem with the kinematic equations, but we can deal with it using something called Quaternions. Now I'm going to omit talking about Quaternions here because it's beyond the scope of what I'm talking about at the moment, but the textbook does give two references if you would like for further information on that. It's numbers 10 and 11 here, given on page 26 of the textbook.